Yeah, so I think we'll just go ahead and start. So welcome everyone to this evening session, evening for the Indian Standard Time, and the new session of the school. We are very glad to have with us Professor Eric Poisson, who will be giving lectures on black hole perturbation theory and discussing relativistic tidal love numbers as well. So I will briefly introduce Professor Poisson before he starts on to his lectures. So Professor Poisson obtained his PhD from University of Alberta, working with Professor Werner Israel on the topic of mass inflation. He then moved to postdoctoral positions at Caltech, and where he was working with Kip Thorne and his group, and later to Washington University in St. Louis to work with Clifford Will's group before joining the faculty at the University of Guelph. Professor Poisson's work is mainly focused on perturbations of black holes and neutron stars in an effort to understand their impact on gravitational waves, impact of tidal interactions in binaries in spirals on the gravitational waves emitted by them. He is an author of two textbooks published by Cambridge University Press, The Relativist Toolkit, which was, I think, published back in 2004, if I'm not incorrect, and a recent book by Professor Clifford Will called as Gravity, Newtonian, Post-Newtonian, and Relativistic. He's also authored a very exhaustive review in the Living Reviews article on dynamics of point particles, motion of point particles in curved spacetimes. Extremely useful review covering a vast range of topics. He's a member of editorial boards for several journals, currently in PRD, and he has been president of the International Society on General Relativity and Gravitation as well. So I think without further ado, we'll just invite Professor Poisson to give his lectures on black hole perturbation theory. Professor Poisson.
Okay, well, thank you very much. I trust that you can hear me and see my screen.
Yes, we are able to see the screen and hear properly. Yeah.
Okay, very good. And thank you very much for the kind introduction and for the invitation to speak at this very fine school. I'm very pleased to be virtually in India for this occasion. For me, it's early morning in wintertime Toronto, so it's very cold. That's why I'm wearing, something warm. And, I had to shovel a lot of snow in the last few days because we had a big snowstorm back on Monday. So anyway, so that's my life. So I will be lecturing on black hole perturbation theory. And let me describe a little bit what I have in mind here. I think roughly what we'll do today, I'll go through a fairly lengthy introduction section with a lot of motivation to explain why it's useful to do perturbation theory. I remember back in the days where I was a student, I learned perturbation theory in quantum mechanics. And I learned in those days that, you can quickly go from, you can quickly exhaust the realm of exact solutions, the harmonic oscillator, the hydrogen atom. And if you want to do anything a little bit more interesting, well, typically you cannot do this with exact solutions. So you have to do perturbations. So you can add a perturbation to your harmonic oscillator to make it unharmonic. You can add a magnetic field to your hydrogen atom and study the Zeeman splitting of spectral lines and all of those things. So the tools of perturbation theory that I first discovered in quantum mechanics turn out to be important, not just in quantum mechanics, but in very many areas of physics, probably all areas of physics, including general relativity. So I'll introduce all of this and motivate this in the first section of the course. And then I'll describe in sort of very general terms what it means to do perturbation theory and general relativity when the quantity that we're interested in is the metric or the curvature of space-time. Then I'll do something a lot more concrete. I'll go directly into perturbations of a very specific space-time, the Schwarzschild space-time, which describes a non-rotating black hole. So I'll spend most of my time, you can gauge that here by the number of dots that corresponds to the number of slides. I'll spend most of my time doing something very concrete and describe what it takes to do perturbation theory around a Schwarzschild black hole. that turns out to have a lot of very interesting applications, like the calculation of gravitational waves. If you're talking about, objects orbiting a black hole, and I'll use that as my sort of main, context for this material. And then I'll say a few words, very few words about how to generalize this to a Kerr black hole. But I won't spend nearly as much effort there because, well, it's a complicated topic, and it's something that we probably would require a lot more time to develop fully. On Saturday, you will do the work. So I'm going to be lecturing today and tomorrow. On Saturday, I'll give you a practical exercise to work through, and you will be calculating the tidal deformation of a black hole. What happens to the black hole when it's put in the presence of other objects that exert a tidal field on the black hole. So I'll give you everything you need, and you will have seen maybe the document, the practicum document that I put together circulated. You'll have access to this. That provides all the background information you'll need to work through the exercise, but this will be you doing the work and learning by doing at the end of those very abstract and long lectures. So my plan on Saturday is that I'll let you do the work. It probably would take, so you have an hour and a half slotted for the course. It probably will take you more time than this to complete the exercise. I hope you will do it. So my plan on Saturday is to let you work on this, and I'll come in maybe an hour later and see if there are questions about it. I'll be very happy to guide you with the work, but I think you'll need to get going first and see how far you can get. So before I get started, just to point out that there's a lot of papers, a lot of literature on black hole perturbation theory. And I think probably one of the best resource out there is a fairly recent paper by Adam Pound and Barry Wardell that contains a very thorough review of everything you need to know about black hole perturbation theory. That includes Schwarzschild, it includes Kerr, with in mind an application to the gravitational cell force. But even if you're not that interested in that, there's a ton of developments regarding black hole perturbation theory that you can find very useful. And in particular, there's a very long list, very exhaustive list of references where you can find everything you need to know about this topic. So I really recommend that you take a look at this, maybe in conjunction to listening to those lectures. Okay, so let's get going. So the first question to ask is, why do perturbation theory? After all, we have a big book of exact solutions to Einstein's field equations that contains probably thousands of exact solutions. Why not just look there for what we need when we're interested in some physical application of the theory? And the answer is that, yeah, it's an amazing feat that we were, we, the community, were able to generate so many exact solutions to the field equations. And, it's a wonderful resource to have those summarized neatly in that book. And it's really an impressive feat mathematically to have come up with all those solutions. But if you're looking at solutions of direct physical relevance, well, there's not, there are not that many. There are not that many solutions that are physically realistic or physically useful. And some are very well known. The Schwarzschild solution is well known. The Kerr solution is well known. The Friedman-Lemaitre, Robertson-Walker solutions of cosmology are well known. The Vaidya solution is one of my favorite, describing accreting or evaporate or radiating black hole. The Majumdar-Papapetrou equation describing extreme charge black holes, any number of those in a static state. That's a known solution. And there's more. There's class of Weyl solutions. There's the symmetric Robinson-Troutman solution that describes a radiation spacetime. There's a number of solutions that have some good physics in them. But, compared to the thousands of solutions that you'll find in the book, that's a very small set. And all of those exact solutions have, symmetries behind them. That's why we were able to derive exact solutions. It's because, there were symmetries that could be exploited in solving the field equations. And therefore, the physical situations described by those solutions are restricted by those symmetries. If we're interested in a situation where the symmetries are not there, for example, think of something that's very relevant for gravitational wave astronomy. Suppose that you want to describe the metric of a spacetime that contains two black holes orbiting around each other, emitting gravitational waves. Well, that's a system that doesn't have spherical symmetry. It doesn't have axial symmetry. It's not static, it's not stationary. So all of those nice symmetries that typically we need to rely on for exact solutions So if we want to describe something like this, and we do, we cannot rely on exact solutions. We have to rely either on numerical solutions, if you solve the entirety of the field equations on a computer, or we rely on perturbation theory. And there are ways of approaching this problem that can be very fruitfully utilized to get some very important insights into this important problem. Another class of problems that I won't talk about in those lectures, but there's a ton of literature on this, and that's also extremely important, is the physics of the early universe. So we always start with assumptions of a uniformity and isotropy. So we say that the universe is homogeneous and isotropic, but that's just the starting approximation. If we want to produce a universe that eventually will have galaxies in it, we have to incorporate some fluctuations that are believed to be of quantum origin. And those fluctuations are, in the early universe, described as a perturbation of those exact solutions. So there's a ton of work that's been devoted to the understanding of how those early fluctuations in the early universe as a perturbation of the Friedmann-Robinson-Walker spacetime, how they evolve in time and eventually grow to become galaxies. So a lot of very important applications of perturbation theory. So now the question is, okay, so how do you set this problem up? So perturbation about what? What's the starting point of the perturbation theory, and what is the expansion parameter of the perturbation theory? And the answers to those questions, well, they vary depending on the context. You can do all sorts of different perturbation theory problems. Here's a few examples. You can think of starting with flat spacetime. So you would do a perturbation of flat spacetime. And you could perturb in powers of the gravitational constant G. And that would be a type of approximation where you assume that gravity is weak, and you can progressively calculate corrections of order G, G squared, G cubed, and all of this. And that framework is called post-Minkowskian theory. And it's all about constructing a perturbation expansion about flat spacetime. Another example along those lines is, well, you still start with Minkowski spacetime, but this time you expand in inverse powers of the speed of light. And that's an assumption about the fact that your spacetime is supposed to vary slowly with time, so that anything that moves in the spacetime is moving slowly compared with the speed of light. So the expansion parameter is really v over c squared, where v is a characteristic velocity for objects in your spacetime. And that would be another situation where you start with Minkowski spacetime and you progressively calculate corrections of order v over c squared and higher order and higher order. And that framework is called post-Newtonian theory. There's been a lot of work over decades on these expansion methods. Another strategy would be to say, well, let's start about another spacetime. Let's start with Schwarzschild spacetime. So here you're assuming that you already have a body, say a black hole, and you want to put things in that spacetime that would be creating a small perturbation. For example, a small companion body. You can have the big black hole. For example, this could be a supermassive black hole at the center of a galaxy. And you would put, a star going around it, or another small black hole or something like that. So the small mass would perturb the big black hole, and you can work out a description of this as an expansion in powers of that perturbing mass. And that is Schwarzschild perturbation theory, and that's going to be the context for most of these lectures. A variation on this theme is that, well, maybe your black hole is actually rotating, so it's not a Schwarzschild black hole, but it's a Kerr black hole. And then you would do the same, you would do the same thing. You would start perturbing the Kerr spacetime, letting the small mass going around it create that perturbation, and you would work out a series expansion in powers of that perturbing mass. And then, as I said before, something you can do also is to perturb around a Friedmann-Lemaitre Robertson-Walker spacetime in cosmology, and model the growth of fluctuations in the universe. And typically, the expansion parameter here would be the fractional change in the density. So the fluctuating part of the density, or pressure, or other fluid variables like this would be your expansion parameters. So these are all sorts of ways where you can do perturbation theory, and the sky's the limit. So anytime you have a spacetime that tends to dominate the physics plus perturbations, well, you can always set up something along those lines. Now, you can consider, the same physical situation in different ways and do different perturbation theories on, with different starting spacetimes, and see how they all, converge together, or converse with each other. So let's go back to that example of a binary black hole orbiting, the two black holes orbiting each other and emitting gravitational waves. Well, there are lots of ways that this situation can be approached in a perturbation theory, direction. And one way would be to suppose that, well, that the orbital separation is large. And if that's true, then that means that the gravitational field is going to be weak between the two bodies. And it's going to be true also that the orbital motion will be slow compared with the speed of light. So that in this regime where the orbital separation is large is a prime example of the fruitfulness of the post-Minkowskian and post-Newtonian methods that I described before, where the starting spacetime is flat, and you just keep on adding perturbations to do a better and better job at describing the the actual gravitational field of the two orbiting black holes. Another approach would be to say, well, maybe your two black holes have a small mass ratio. So maybe this black hole is very small compared to that one. And maybe in this situation, it makes sense for the starting point to be the Schwarzschild spacetime of the big black hole, or the Kerr spacetime of the big black hole, and to let the smaller object create a perturbation on top of that spacetime. So in this regime of small mass ratio, you have two ways of setting up the perturbation, either in this way, starting from flat spacetime, or either this way, starting from the Schwarzschild spacetime. So for the two approaches to be comparable, of course, you have to have a small mass ratio, but you also, but to compare the answers you would get from both approaches, you can take the limit of the results you find here and so that approach here doesn't require the separation to be large between the big black hole and a small black hole. But if you apply your results to a situation where the orbital separation is large, then you can compare your answers to the ones that would be derived in post-Newtonian theory. Alternatively, you can take the situation over here where you do assume that the orbital separation is large, but you don't need to assume a small mass ratio. But you can take those results and apply them to a small mass ratio situation and compare your answers to those of perturbation theory. So these kinds of games have been played, and they're very, very useful because you can check results, you can calibrate results, and sometimes you can derive things on this side that are hard to derive, but are easy to derive here, and vice versa. So you can feed information back and forth between the two ways of doing perturbation theory, because some of the things are easier to calculate on this side, some of the things are easier to calculate on this side, and you can pass information across, that sort of fictitious boundary between the two. So different ways of looking at the same physical situation, setting up two different perturbation theory problems can be very fruitful at reinforcing one another. And something that people have discovered recently is that, in fact, you can take the results of cell force and black hole perturbation theory, arbitrarily crank up the mass ratio to be something which is not that small, and get something which compares extremely well with post-Newtonian theory. So you find sometimes that the regime of the domain of validity of your approximation extends what you thought it should be. You have some leeway in going beyond what you think should be reasonable and get results that are still factually and factually accurate. So sometimes you're happily surprised by things like that. So I won't dwell on this, but another approach, of course, is to solve the full set of equations without approximation, except for discretizing them and putting them on a supercomputer. So you can approach the problem with numerical relativity. So here, in principle, you have access to the full correct answer, albeit generated numerically. And again, you can pass information back and forth because you can also play play those games where you take numerical relativity, you apply them to fairly large separation, or you apply those results of numerical relativity to small mass ratios. And again, that allows you to do some cross comparisons between different approaches.
So, Professor Poisson,
Yep.
May I just interrupt for a second? There seems to be a question in the chat box.
Yep.
By Sajad. He's asking, where does multiple expansion fit into the figure that is on display? Is that right, Sajad? If you want to ask anything. So the question is, where does multiple expansion fit into the figure that is on display?
Okay, no, a very good question. So the multiple expansion is typically something you would apply. So it's incorporated in this, it's incorporated in this as well. And it's, I would say it's an approximation on top of those approximations, where what you would do is to go to infinity and see what you get at infinity. And of course, what you get at infinity are gravitational waves coming out. And you would do an expansion of those waves in multiple moments. And that's essentially another expansion in powers of v over c squared. So it's sort of already incorporated in this. It can be incorporated on top of the perturbation theory expansion, but it's really something that typically would be done only if you're interested in the gravitational waves at infinity. So I hope that answers your question.
Sajid, I hope that answered. Yeah, okay, sure. Please go ahead, Professor. I think it's...
Okay, I see that Chandra has his hand up.
Yeah, a very quick question. So, just about this, the cartoon or the image about this post-Newtonian, post-Minkowskian figure. So this flat space-time, this is far from the source, right? I mean,
yes. So typically, yeah. So you assume that this is a description that would be good, not very close to each black hole, obviously, but right. As soon as you're clearing out of the immediate vicinity of the black hole, then it becomes decent. And yeah, so it would be good, in between the bodies and far away from each body.
Right. Okay, thanks. Yeah.
Right. So in practice, when you do post-Newtonian theory, you don't really know that you're dealing with black holes. You just treat them as point masses. And the way that you incorporate the information that those are black holes is when you consider the multiple moments of each black hole, and you put information about structure, body structure into the gravitational field around each body.
Yeah, thanks. Yeah.
Okay, so yeah, thank you for the questions, and please keep on asking them. I think it's a lot more pleasant for everybody if you keep asking questions.
Yeah, there in fact seems to be another question by Lakshman. I think Lakshman,
Okay.
you can just go ahead and ask.
And speak up, yep.
Yeah, you can unmute and ask. Okay, I think there seems to, I will just read off the question.
Yeah.
Is asking, when taking the high mass ratio limit of post-Newtonian theory, we are into the strong field regime of massive black holes. So the PN approximation is not valid. So his question is, till what mass ratio can we take the high mass ratio limit of PN to converge at black hole perturbation theory?
Yeah, so that's a very good question. And it's also a very delicate question because, so when I take an expansion in powers of the mass ratio, of course, I imagine that M over big M, little m over big M must be something small, but who knows how small it must be for the approximation to make sense. Is it 10 to minus 3? Is it 10 to minus 6? Is it 10 to minus 9? So in principle, you can answer the question by, well, if you calculated the first order term, you can go and calculate the second order term and figure out, if it's very small compared to the first order term, and you can sort of guide yourself this way. But the way this is really done in practice is to really compare with numerical relativity. So what people try to do is to say, let's take numerical relativity simulations with a mass ratio of 1 to 10. And let's see how we can make it fit to results from black hole perturbation theory. And let's measure the error between the two. And what is found is that even at the mass ratio of 1 to 10, well, the error is still pretty decent. It's not, it's not perfect, obviously, but the error is not bad. If they could do 1 to 100, then you could still do the comparison, and you would find that the errors have become much smaller. So in this way, so because you can test across different methods like this, you can really understand the limitations of each approximation, and that really helps in gauging the accuracy of each method. I hope that answered the question.
I believe so. Yeah. Yeah.
Okay, anything else before I move on?
No, I think we can proceed. Yeah.
Okay, very good. So, okay, so let me move on. I think I've made my point here. Yeah, and I have to thank Lior Barak. This plot has become very famous, and Lior produced it several years ago. Okay, so let me start about introducing the main ideas behind perturbation theory. And I'll do it, very simply first in a very simple setting, and then I'll move on to GR as we keep going. And I would say that if you want to learn everything about perturbation methods in applied mathematics, I can think of no better book than this one here by Bender and Horsag. It's called Advanced Mathematical Methods for Scientists and Engineers. And I think it's one of the best math books I've ever read because it's very practical and it really teaches you methods to do actual calculations. It's very practical. Okay, so let's consider a very simple problem, algebraic problem where you're asked to solve this equation over here, where epsilon is some given number that's given to you that is small, for example, 10 to minus 3 or something like that. And so you need to find a solution to this with the condition that x has to be positive. And you look at this and you see it's a quartic equation. You know that you can actually find a solution to a quartic equation, but if you've ever stared at that solution, it's extremely complicated. Lots of strange square roots with strange powers. It's very unwieldy, and it really doesn't give you much insight into the actual answer. So here's an example, because epsilon is small, of where perturbation theory can tell you more, because it can tell you something much simpler than the exact solution. So what do you do about this? Well, the trick is to not consider just one value of epsilon, but just consider a range of values. So the way that I formulate this is to say, let's consider a one parameter family of solutions where X would depend continuously on that parameter lambda. And lambda is imagined to range from 0 to the value epsilon that's given to you. So in perturbation theory, we always set things up in such a way where we have a one parameter family of solutions where the parameter allows you to go from the unperturbed solution and you can crank it up all the way up to the actual perturbation that you're interested for that specific value of epsilon. So it's a very useful way of thinking about this. And it's very useful to think of a solution that ranges from the unperturbed to the perturbed in a continuous way. So what do you do? Well, you postulate a power series expansion in powers of that parameter. Lambda, of course, is guaranteed to be small. So that is, very sensible to do. So you just postulate a power series expansion like this. Each coefficient here can be expressed as a derivative of that one parameter family, with respect to the parameter lambda. And then, well, it becomes very simple. So one, of course, here is the unperturbed solution that I'm looking for, the one that is positive. And the procedure is very simple. You just plug that into here. You expand everything in powers of lambda. You match the powers of lambda. And you end up with, equations for x1, equations for x2, x3, and x4. And you can keep going as far as you want. So in this problem, for example, and when you're done, you plug in, lambda is equal to epsilon, and now you have your solution for the actual perturbed problem for the given value of epsilon. So if you do this as an exercise, you'll find those expressions for the xn coefficients. And if you're given epsilon to be 0.1, for example, well, when I solve the problem numerically and when I compare it to the approximate solution, keeping 4 terms in the expansion like this, I find that the error is extremely small, probably smaller than I need, and almost equivalent to machine accuracy on a computer. So that tells me that keeping 4 terms in the expansion is probably plenty good for my purposes, any purposes I might have, even for an epsilon that on the face of it is not that small, right? It's 0.1 as opposed to being 10 to the minus 3 or 10 to the minus 6 or something like that. So that, that procedure is, very straightforward, very simple. It returns a solution that has simplicity in its favor. And on top of that, well, you have the solution not just for one value of epsilon, but you have it for a whole range of values. So it's, it is
so
actually
Poisson,
pretty...
Yep. Sorry, there is a question asking how close is, I think this is pertaining to the example you're showing. How close is it to the exact solution rather than the numerical one? I think this is...
Yeah, no, thank you for asking. So I don't know. I didn't calculate the exact solution. I think I did the numerical solution up to machine accuracy. So I would think that it's probably as good as it needs to be. So I think here, so I would say that a good guess would be that the numerical solution and the exact solution are probably 1 part in 10 to the 16, accurate. And this is basically 2 orders of magnitude larger than that. So that, I think that gives you an idea.
Okay.
But yeah, but that's just a guess.
Sure, yeah.
I don't think I haven't done the calculation. All right, no, thanks for the question. So the main issue when you do something like this is to ask about convergence of this series. And typically the answer is that it's not true that keeping on generating more terms would necessarily produce a better answer. If you have a convergent series, that might happen, but typically the series that you're generating is asymptotic. And what this means is that for asymptotic series is that, well, you calculate a few terms, you get progressively a better answer in terms of a numerical comparison of this sort here. But eventually, as you keep on generating more terms in the asymptotic expansion, you find that the answer gets worse. And what this means is that the asymptotic series, well, doesn't converge, so it doesn't get better and better. So eventually it starts, deviating more strongly. And the rule of thumb is that, well, you can use asymptotic series usefully because they still give you a very decent approximation. But, it has to be truncated at the right place to give you the optimum answer. And where that is depends on the problem, depends on context, depends on the numerical value of the perturbing parameter. So it's a bit of an art form to decide how to best use asymptotic series in a perturbation game like this. And that's part of the whole, apparatus where you have to be sure not to ask too much, not to ask convergence, and understand that what you're doing is pragmatic. It's not something that that can achieve everything for you. On the other hand, even if you knew that your series were converging, well, sometimes you get converging series that are completely useless because in order to achieve convergence to a certain numerical accuracy, you would need millions of terms, and you don't have in you the power of computing millions of terms. So sometimes asymptotic series are far more useful than converging series because they give you better answers with fewer terms. So as you learn to work in this field, you tend to recognize the value of asymptotic series and not to be too hung up on the on demanding that series like this should always converge. All right, so that was the example from algebra. Are there any questions before I move on? No? Okay. So here's a slightly, yeah, I see Chandra has a question.
Can you comment on the presence of log terms on?
Oh, yeah.
Yeah.
Right. So yeah, so it could happen that a straightforward power expansion like this actually is not adequate. And it could be that, for example, you have fractional powers showing up. It could be that you have log terms showing up. So that can happen, and it does happen in post-Newtonian theory, for example. There are log terms that show up. And that's the kind of thing that, well, you would recognize as you keep proceeding like this, you would recognize that your equations don't match up as you substitute the ansatz or the assumed power expansion. When you assume, when you plug that into that problem, it might be that there's some terms that don't match up, and you would need to modify accordingly. And how to do that in practice, well, that could be difficult to determine. But yeah, sometimes you have to be very flexible in what you assume to be the right power expansion. And sometimes, as Chandra pointed out, you can, you have to introduce log terms in order to actually do the job of solving the equation. So yeah, so the framework is, needs flexibility in order to, in order to be successful. Okay, so let's consider a slightly more complicated example where now instead of solving an algebraic equation, we'll go into solving a differential equation. So let's assume that we're given a second order differential equation. So y double prime and a term like this, 1 minus epsilon x times y. I want to solve that equation with boundary conditions that the solution is equal to 1 at one boundary and 0 at the other boundary, which is at pi over 2. And so we would like to have a solution to that equation. When we look at all the books on differential equations, we can find that, well, there is in fact an exact solution to that equation in terms of Airy functions. But Airy functions are complicated functions. They're implicitly defined. They're special functions for which the properties are listed in books. So maybe that's not quite what you want. Maybe you would like to have a simpler representation of the function that you can use that would simplify your life. And here it would be a matter of relying on the fact that epsilon is small, and solving the equation for epsilon equals 0 is actually very simple. So the idea would be to employ the tools of perturbation theory, where you would start from the with the unperturbed problem, set epsilon equal to 0, and then crank out, crank out corrections to this. So again, the idea is that we would take our dependent variable y, we would make it now a function of an independent variable x and a function of a parameter lambda. So we would consider a one parameter family of solutions. Lambda would be assumed to be ranging from the unperturbed situation to the perturbed situation, going from 0 to epsilon. And we would postulate a power series of the same form we had before, except that now that the coefficients are now functions of x. The unperturbed solution, obviously, that satisfies those boundary conditions is going to be the cosine function. And because I want the full solution to also satisfy those boundary conditions, each coefficient here has to satisfy 0 boundary conditions at both boundaries. So the procedure, again, very straightforward. We would plug that into the differential equation, equate, set lambda equal to 0, set lambda is equal to epsilon, match powers of epsilon, and then we would get a whole bunch of differential equations, first for y1, then for y2, then for y3, and we could solve step by step for each one of those corrections. And if you apply the procedure, well, first of all, you can find that y1 takes on this form, y2 takes on that form, and I could calculate the next one, which I think I did, but I didn't want to display it here because they get progressively a little bit longer to display. So again, a very strict, yeah.
There is a question. Sriram, you want to ask it? So the question is there any equivalence to the Wkb approximation?
Yes, so let me try to remember. I think, yes. So I think so the Wkb approximation would have an epsilon like this, but the x would be replaced by some arbitrary function of x. That would be the potential. So yeah, so I think you're right to suggest that this is a specialization or a special case of the full Wkb approximation, where instead of an x here, you would have some arbitrary function of x. So yeah, very good question.
Okay.
All right, so again, so the procedure is very straightforward. Again, it could be that for any particular implementation of this, you would realize that the straightforward power expansion is not adequate. You need to modify it, maybe with fractional powers, maybe with log terms. So all of those caveats enter here as well. Here also, typically you would get an asymptotic series, not a converging series. Another thing you would have to be careful about is whether the approximation is uniform across the domain. So here the domain is between 0 and pi over 2. Is it true that that the approximation is uniform over that domain? Those are all issues that arise in this context. For example, if the domain were not bounded, you see that x is growing, x squared is growing. You have an x fourth here, you have an x squared here. So you would have to worry about maybe the approximation being good in part of the domain, but not being good elsewhere. So all of those things are things that people need to worry about when you do perturbation theory. But in this context here, in fact, the approximation is very good. So I think here, I didn't pick a value for epsilon, but I just note that numerically y1 is bounded, y2 is bounded, y3 is bounded, and those bounds become progressively smaller as you increase the order. So that's an approximation that in fact is uniformly good in the domain and is a very good asymptotic series because it gives you numerically accurate answers pretty quickly. You don't need to keep doing this forever to get an answer that becomes adequate if epsilon is fairly small. All right, let me introduce some other caveats because the straightforward expansion that I introduced before doesn't always work. Sometimes it fails spectacularly. One issue is often associated with that idea of uniformity. So the approximation might be very good for small x. It might become progressively bad as x increases. So there's issues that can arise like that. Another class of examples is when your epsilon actually is put in front of, in the algebra problem, in front of the largest term, the largest power, or in the case of a differential equation where it's put in front of the largest derivative. And this is an area that's very subtle because even though it's still true that epsilon is small, the way that epsilon is placed here means that the unperturbed problem and the perturbed problem have very different characters. Here, the unperturbed problem is cubic, so you get 3 solutions. The unperturbed problem is quartic, so you get 4. So the character of the problem has changed completely, even though epsilon is small. And what this means in practice is that 3 of your solutions are going to be perturbative. They're going to be slightly disturbed from epsilon equals 0. They will acquire small corrections. But 1 of your solution is going to be non-perturbative. It's going to have singular behavior as epsilon goes to 0. Same thing over here. You've changed the character of the equation. In the unperturbed problem, it's a first order differential equation. For the perturbed problem, it's actually second order. So again, the number of solutions changes, the number of boundary conditions that are required to get an exact solution changes. So when epsilon is featured in this way, the straightforward expansion method just fails. It just doesn't work. And that's the realm of what's known as singular perturbation theory. That's a beautiful body of work that you can read all about in Bender and Horsack, for example. And the techniques required to solve singular perturbation problems like this are very rich, very beautiful, very powerful. There's a range of things you can do, scale transformation. You can break up your domain into multi-domains. That's the boundary layer theory. That's extremely useful and required in fluid problems, for example. You can do a multi-scale analysis that's related to this, where you break up your domain and introduce different scales. There are all sorts of methods that can be introduced in this case that make the mathematics a lot more interesting, but also a lot more finicky and a lot more, delicate to deal with, but, very beautiful stuff that I take a lot of pleasure working through whenever I have a chance. It's very, very nice stuff. Okay, so I think I'm about to move on. Any questions at this stage? Okay, I'm getting done. So let's move on. So I want to apply those ideas to general relativity. And I think I'll do it first in a simple context that I'm sure you will have seen before. And that's linearized general relativity, the idea that you can start with Minkowski spacetime, consider weak field situations, and calculate a correction on top of Minkowski, and have a spacetime metric that's going to be expressed as Minkowski plus corrections. So that's something that I think a lot of people probably have, a lot of students have worked through in their first course in GR. So the context will appear familiar. I just want to frame this in the sort of language that I've described up to now. Okay, so here's the goal. We want to solve the Einstein field equations. We have the Einstein tensor on the left as a functional of the metric. We have the energy momentum tensor on the right, which also depends on the metric. So it's a complicated system of second order nonlinear partial differential equations. So it's a task to solve this. I want to make an assumption that the energy momentum tensor in some sense is small. And I will take that to be my epsilon. So a typical component of the energy momentum tensor, for example, will be multiplied by a mass, will be coming with the mass. If I'm describing the energy momentum tensor of a point mass, for example, so epsilon might be thought of as the mass. And I want to think of this as a small parameter and use it as an expansion parameter. So the main assumption then is that this will create a small deviation from flat space-time, and I want to rely on that smallness. So what do we do? Well, we apply the ideas of perturbation theory. We say, well, let's postulate the existence of a one parameter family of solutions, namely one parameter family of metrics. The metric will depend on the space-time coordinates x, but it will also depend on the parameter in a continuous way. We will let the parameter range from 0, the unperturbed situation, to epsilon, the perturbed situation. And we will postulate a power series of that form, where we'll have a coefficient in front of lambda, another coefficient in front of lambda squared, and in principle, this keeps on going. Each coefficient here can be thought of as the derivative, and the nth derivative of the metric with respect to the parameter evaluated at lambda equals 0. So then it becomes more or less the same procedure as before, except that the implementation is more complicated because the equations are more complicated. But basically, we plug this assumed form of the metric over here in the Einstein tensor, over here in the energy momentum tensor. We set lambda equals to epsilon. We match all powers of epsilon, and we get a sequence of equations for P1, then for P2, then for P3 if we wanted to go that far. So it's the same spirit, the same sort of practical approach, and in principle it's the same story, except that, well, there's some complications that arise because we're dealing with GR and not some simpler system of differential equations. And one complication, and that tends to create confusion and irritation sometimes, is the fact that the space-time coordinates are not absolute, right? I mean, you can change the coordinates as you change the system. So what I mean by that is that we can consider the coordinate system to also be a one parameter family of coordinate systems. You can, as you range from the unperturbed situation to the perturbed situation, letting lambda go from 0 to epsilon, you can continually tweak the coordinates and make them themselves, the coordinates, functions of lambda. That's allowed because, GR is all about the arbitrariness of coordinates. We have diffeomorphism invariance, and that sort of thing here is not only allowed, it's almost, mandatory. You have to consider doing something like this. And the reason why it's actually a good idea to do something like that is that you can use this coordinate freedom to simplify the equations for each one of those perturbation variables, P1, P2, and so on. Excuse me. So that's a complication, but in some sense, it's a welcome complication because it gives you more freedom to simplify things. On the other hand, it's a little bit of a nuisance because you really must take that into account as you do your perturbation theory. So what people do here is to say, well, in order to restrict this freedom that we have here, or at least use it to our advantage, what we're going to do is to impose a coordinate condition. We're going to impose requirements on these things that will produce what we want in terms of simplification. So here I say coordinate condition. The language that's typically used here is gauge condition. The words gauge condition tend to bring a parallel with electromagnetism, where you have potentials and you have a gauge freedom, and you can impose gauge conditions on the potentials to make them unique, that sort of thing. So there's a good correspondence between those two things. But I think there's a bit of a danger in relying too much on the language, and because we can lose track of the fact that we're really talking about the coordinate condition here. So I think there's a danger in insisting too much on the association between gauge and electromagnetism and coordinate issues in GR. I mean, it's a useful parallel, but it comes with a little bit of danger sometimes when, when you don't give enough thought to the fact that it's not quite the same thing, really. Anyway, forget about that. I'm just making a big deal out of something that probably shouldn't be a big deal. All right, so when we apply all of this to linearized GR, what we tend to do here is to say, okay, let's consider not P1, but a trace reversed version of P1. So we consider this combination here, and we call that H. And basically what I've done here is to take P1 and remove the trace of P1 and through an application of the Minkowski metric over here. So that's a technical thing that we do to achieve simplicity. Then we impose a coordinate condition, and the coordinate condition is actually disguised as a condition on the potential. So that's why it looks like a gauge condition. But it's really a coordinate condition because you can prove that imposing this is actually making a requirement on that, freedom that you have here in changing the coordinate system continuously as you go from 0 to epsilon. If you do this, and it's a choice, we don't have to do it, but we can. When we do it, we find that each H alpha beta here satisfies a very simple looking wave equation in Minkowski spacetime. That's the wave operator in Minkowski spacetime acting on those potentials being equated to the energy momentum tensor evaluated with the Minkowski metric. Those are the standard field equations of linearized gravity, and their simplicity means that we can find solutions easily. And that simplicity was achieved by, exploiting the freedom that's given to us here by those, by this coordinate adjustment as we go from lambda equals 0 to lambda equals epsilon. Okay, so I think you will have seen this in one way, in one guise or another in your education. We can think of now doing exactly the same thing, but now instead of starting from Minkowski, we can think of starting from any other background metric. In principle, we can play the game starting from any background metric, for example, Schwarzschild. Why not? For simplicity here, and it's just to state the equations and state the results a little bit more simply, I will assume that the background metric is itself a vacuum solution to the field equations. That would apply to a black hole spacetime, so that's fine. If I wanted to do cosmology, that would not be true. So I would have to modify certain things in the discussion to acknowledge the fact that my starting metric is not a vacuum solution. But things do simplify a bit if you assume that the starting spacetime is a vacuum solution, and I'll do that here. And as before, I will assume that the source of the perturbation is some object that you've inserted, or some matter that you've inserted in that vacuum spacetime that has an energy momentum tensor that typically has, components that are small. So I'll put an epsilon parameter in front of it, and that's going to serve as a bookkeeping parameter for my expansion. So what do? Well, we do what we did before. We start with the starting metric. So first of all, we make the actual metric of spacetime a one parameter family of metrics. We let lambda range continuously from 0 to epsilon. We have a background metric for lambda equals to 0, and then we have a first order correction, second order correction, and then in principle we could keep going. And chances are that log terms would have to be included at some stage here, but let's not worry about that. And then what would we do? Well, we would plug in that assumed form from the metric inside the Einstein tensor. So the Einstein tensor would be evaluated for that metric. And then, of course, to first order, we would get, or to 0th order, we would get 0 because of that assumption. And then we would pick up a first order correction, which I'm calling G dot. So G dot here is going to be notation for the first lambda derivative of the full Einstein tensor evaluated at 0. So that's the same sort of derivative notation that I've used before in all of the perturbation problems that we've looked at. G dot, the first order term in the Einstein tensor would be let me finish the thought. G dot would be a functional of the background metric and a functional of the first order metric perturbation. So it would depend, it would have a dependence on the background and a dependence on the perturbation. And then in principle, this would keep going. The energy momentum tensor, because it already comes with an epsilon in front of it, would start at leading order and it would be evaluated on the background metric. Yep, so there was a question?
Yeah, there's a question from Aditya. Aditya, can you just go ahead and ask the question?
Yeah, thanks. So I wanted to ask about your background being a vacuum solution. So in
Yeah.
case it is not, what changes? T alpha beta will have a zeroth order term. Is that it?
Yeah.
Or something?
So yeah, that's right. So there would be zeroth order terms here, and there would be zeroth order terms here as well. And the main thing that this would change is the fact that the dependence on the background would, so the zero that, let me see if I can say this straight. Yeah, so there would be zeroth order terms. And yeah, I think that's basically it. So it just, yeah, I'm trying to remember why I was trying to make a big deal out of this. It just changes. Yeah, I mean, that's basically all there is, except that the coupling between background and perturbation is a bit more complicated. The coupling between the matter variables and the perturbation variables, all of that becomes a little more intricate. But yeah, but those are all technical complications. Conceptually, the only difference is that, yeah, you would have zeroth order terms added to those equations here.
Thanks.
Anything else?
Yeah,
Okay,
there is
let's. Yep.
that won't the gauge conditions or transformations become complicated beyond a linear order?
Yes, so it becomes more complicated. So imposing the coordinate condition at first order tends to be straightforward, although sometimes not that straightforward, because you're given a lot of freedom, so you want to make the right decisions, and sometimes you have to do a bit of a trial and error to do that. At second order, well, you would have more complicated coordinate conditions that would depend on the choices you made at first order. So yes, everything gets more complicated as you proceed to higher order. And that's why it's difficult. I mean, so perturbation theory at first order is straightforward. Perturbation theory at second order can be a lot more complicated. I'm not aware of anybody who's done perturbation theory at third order in any practical sense of actually cranking out results at third order. Maybe some people have been brave and done that, but yeah, it just gets very complicated. I see another question. Chandra? No, sorry. You're muted.
I think it was Shriram, and Shriram, there's anything else you wanted to ask? So I think you've already answered, because he has typed the question in the chat as well, Professor Poisson.
Okay.
That was the
anyway,
question.
We can always come back to it if you're not satisfied. But yeah, of course, everything gets increasingly complicated as you proceed to higher order. It was true for the algebra problem, but it's more so in this case here, where the starting equations are a lot more complicated and messy. Okay, but in principle, so I really insist that the ideas are the same. And if all you want to do is first order perturbation theory, then what you end up with is a perturbed Einstein tensor on the left-hand side that depends on the background spacetime. So the differential operator that you will end up having here will depend on the background spacetime, but that differential operator will be acting on the perturbation, and it will be acting linearly on the perturbation. So it becomes a system of linear differential equations, partial differential equations for the perturbation, with a source term that's constructed from the background metric. So the energy momentum tensor here doesn't require perturbation information, it only requires background information. And that has to do with that structure over here that says that because the energy momentum tensor already comes with a factor of epsilon explicitly or implicitly, because it's assumed to be small, when I crank out the perturbation here, I can stop at leading order because it will match the first order calculation of the Einstein tensor, the leading order term being 0 by this assumption. So that's why I wanted to make the assumption, because that's when everything becomes very nice and simple. And that's when you end up with that simple, well, here it's very implicitly expressed, but it's simple because it's a linear equation for P1 with an explicit source term that knowing only the background spacetime. So that's the structure that emerges. And that's why, and that simplicity of structure is something that allows us to make progress. And we'll rely on that, of course, in the rest of the lectures. I see a question.
Hi, can you hear me now? This is Sriram.
I can, yep.
Okay. In the context of cosmology, you can decompose these perturbations, what you have referred to as P alpha beta, because of the symmetry of the background, into scalar vector tensor. Yep. Will you be able to comment about that in a more generic, such decomposition of generic spacetimes?
I will say some words about this, but I won't describe the cosmological case. I will do it, though, for Schwarzschild. So in cosmology, typically you would start with a flat background. So you would do a decomposition in terms of plane waves first. But then you would do a tensor decomposition, as you say, into scalar vector and tensor pieces. So in Schwarzschild, we proceed differently because we start with spherical symmetry instead of planar symmetry. So instead of doing, but we would use the static nature of the space-time to do a decomposition in terms of frequency, so a Fourier transform. But then we would do, because of the spherical symmetry, we would decompose everything in terms of spherical harmonics. So it's a similar idea, but a different functional basis, because we're using different symmetries as our starting point. And I'll have a very extensive discussion of this for the Schwarzschild case.
I understand. Thank you.
Okay. Yeah, but those decompositions are very important because they allow simplification, they allow decoupling, they allow us to make progress a lot more easily than if you didn't have those underlying symmetries. Okay, so conceptually, this is the structure of the perturbation equations. And again, this coordinate freedom that we had in the linearized case, well, we have an analog of this when we start from a non-flat metric. So here also we have the freedom to continually adjust the coordinates as we go from unperturbed to the perturbed situation. And in order to make those equations well posed and to get unique solutions out of them, we have to impose a coordinate condition, which typically tends to be 4 conditions. You know, there's an index here, 4 conditions on those metric variables that, well, we could set to 0. We have 4 equations for those that will then pin down the perturbation variables uniquely. And I'll come back to this theme as we proceed when we do something a bit more concrete for Schwarzschild in tomorrow's lecture. So that's the idea, and I think what I was hoping would emerge here, and I hope that you sort of saw that, is that the ideas to do perturbation theory are the same whether you do algebra, differential equations, or general relativity. And if you think of your quantum mechanics course, when maybe you did perturbation theory also, well, it was the same sort of idea, where you take your ket vector, you expand it in powers of epsilon, you take your energy eigenvalue, you do an expansion like this. So all of those ideas are shared, and they apply just as well regardless of context, and they apply just as well to GR. So that's the main message here, that there's a systematic way of doing this that is the same regardless of context. So that's the main message behind this part of the lecture. For the last few slides, and to finish up today, I thought it would be nice to talk about the differential geometry of perturbation theory. And I'm just mentioning this here as a curiosity and as something that may appeal to you if you like differential geometry, if you like those geometrical ways of seeing things. In GR, we tend to be really keen on seeing everything through geometry. And it turns out that there's a very nice geometrical structure behind this, this perturbation theory business that I think sheds a lot of nice conceptual light on the basic problem, and sometimes can even help in the technical aspects. But I think it's really good for setting up the conceptual aspects of this. And it's kind of pretty. I don't tend to dwell on this when I do my work in perturbation theory, because I tend to focus on the practicalities of it. But once in a while, it's good to think about the deeper conceptual aspects of all this. And I just wanted to give you a flavor of this as, as a way of finishing up this lecture. So let's think a little bit more abstractly about what we've done. We've been talking about a space-time that is taken from a background configuration to a perturbed configuration, as lambda was going from 0 to epsilon. So what's a space-time? Well, a space-time is a manifold and a metric. So as we go from the background space-time, we're going from a background manifold and a background metric. And when we go to the perturbed space-time, we reach a perturbed manifold and a perturbed metric. So the point is that, as we think in space-time, abstractly, we have to think of it as the union of a manifold and a metric. And if we perturb one, we perturb the other. So we have to recognize that the perturbed manifold might be different from the original manifold, as the metric is different from the original metric. So the way to describe this formally is to think of this, again, as a one-parameter family of spacetimes. And that means that we're going to be adjusting the metric and the manifold from lambda equals 0 to lambda equals epsilon in a continuous manner. So we're really describing a one-parameter family of spacetimes, as we have done everything else in this lecture. It's very useful, a little bit strange, but it's very useful to think of lambda as an extra dimension. And think of this as describing a 5D manifold with a new direction given by lambda. I'll draw a picture of this in a moment. So the entire family of spacetimes here, the one-parameter family, can be embedded in a 5-dimensional spacetime with lambda being the extra dimension. Now, the metric itself is still 4-dimensional, so I don't consider, metric directions in the lambda direction, but I want to think of the entire manifold as being 5-dimensional, with lambda being the extra direction. So we can imagine moving through this manifold as we go from the background configuration to the perturbed configuration. So it gives us a very nice mental picture of what we're trying to do. And the whole game of perturbation theory then is to define the perturbation of some tensorial quantity, for example, the Riemann tensor. You might think of the Riemann tensor living in a background spacetime that's been perturbed by the perturbation. And we want to define and calculate this perturbation. So in this language over here, well, what we want to define is a one-parameter family of quantities Q. For example, the Riemann tensor defined as a one-parameter family of Riemann tensors with lambda the parameter, or now a Riemann tensor that's defined in a 5-dimensional manifold. We want to define this for the entire 5-dimensional manifold and then compare this to that. And the difference between the two, when lambda is set equal to epsilon, would be a definition of the perturbation. So I think the ideas are pretty clear, but what makes the practicality of this a little bit, delicate and sometimes a little bit, irritating is the idea of that coordinate freedom that I've talked about. But the 5-dimensional language gives us a picture of what this is all about. And that's what I mean here by the identification map. Let me explain all of this in terms of that diagram. Here's the 5-dimensional manifold, and that 5-dimensional manifold is foliated by sections of constant lambda. So this is the background manifold with the background metric on it. This is one member of the foliation. This is another leaf of the foliation. And up here, we have the perturbed manifold when lambda is equal to epsilon. In order to do anything and start defining perturbation, what we want to do is to compare a quantity up here to a quantity down here and say that the quantities are being evaluated at the same point. But now we have to define what it means, same point. We have to decide what it means to compare a quantity down here to a quantity up here because, well, it's not the same point, right? I mean, we're talking about very different points in that 5-dimensional manifold. So in order to establish any comparison between quantities up here and quantities down here, we have to establish a correspondence of points between this manifold, submanifold, I should say, and this submanifold up here. So the way to do this is to introduce in the 5D manifold a vector field that will be pointing from this leaf of the foliation up to that leaf of the foliation. So we introduce this vector field V, that's a 5-dimensional vector field, which is taking us from the unperturbed manifold to the perturbed manifold. So it's a vector field that roughly points up. And here I'm saying that it has to be transverse, it has to go across the leaves, and it cannot be tangent to the leaves because that would, that would stall the progression from the unperturbed spacetime to the perturbed spacetime. From the vector field, we can construct the integral curves. So I'm denoting them phi of lambda here. The integral curves of the manifold, of the vector field, are what I'm drawing here in red. And I'm going to use those integral curves as a way of establishing a correspondence between this point here on the unperturbed spacetime and that point up here in the perturbed spacetime. So what I'm saying here is that in order to establish a comparison between quantities up here and quantities down here, I need to establish a correspondence between points, an identification between points. And I'm going to use the integral curves to do that. And the integral curves are going to be defined through that new structure that I have to introduce, which is that vector field V. And the attitude will be that, okay, I'm going to use the integral curve to say that the point P naught here will be identified with the point P epsilon up here because they both live on the same integral curve. I'm going to have a correspondence between those 2 points, those 2 points. So I'm assuming here that the vector field is non-singular, that the integral curves define a congruence, so they don't intersect anywhere. And I can use those integral curves then to establish a correspondence between this point and all the other points. And with that extra structure in the 5-dimensional manifold, I can meaningfully say, calculate or, talk about the difference between a tensor up here and a tensor down here. And I can define that to be the perturbation of the tensor, the original tensor. The main point here is that in order to even talk about a perturbation, in order to talk about differences between quantities up here and quantities down here, I have to establish a correspondence between points here and point there. So in order to even define a perturbation, I have to introduce those integral curves. I have to introduce this additional structure of a vector field in that 5-dimensional spacetime. So you see the sort of nice geometrical picture that we have of this. And then, well, you can go ahead and define a perturbation. So the first derivative of that tensor Q, think of this as the Riemann tensor that has now become a function of the parameter, a one parameter family of Riemann tensors. The perturbation will be defined as we did before as the partial derivative with respect to lambda. But now that partial derivative acquires a geometrical meaning, because it really means take a Lie derivative along the vector field that we've introduced. Because that vector field that we've introduced, by definition, is transport along lambda. So a derivative with respect to lambda is, by definition, keeping the x coordinates fixed. A derivative with respect to lambda, keeping x fixed, is really a Lie derivative. With respect to that vector field V. And here I have to assume, sorry about that, I have to assume that you know about Lie derivatives and so on. If you don't, forget about it. We'll never come back to this later on. So this is just for cultural purposes more than anything. Okay, but now that we have that, now that we have this nice way of thinking about this, we have a new way, and I think a really powerful way of thinking about what it means to have all of this coordinate freedom at our disposal and what it means to impose a gauge, to impose a choice, a coordinate condition or a gauge condition. What I'm saying here is that, well, here I introduced one vector field in that 5-dimensional spacetime, and I had freedom in doing this. I could have picked any vector field. I could have picked any system of integral curves. So I did it one way. Suppose I do it some other way, introduce a different vector field W with integral curves that are very different psi. So now I would have a setup like this, except that the vector field would be different, the integral curves would be different, and that would mean that a point down here would be associated now with a different point up here. So that's what I'm illustrating here. I have one point in the unperturbed manifold that is taken over to that point under one set of integral curves, but is taken over to that point, different point, under the action of a different set of integral curves. So two different vector fields, two different set of integral curves, and therefore two different points associated with the same initial point on the background manifold. That's the coordinate freedom. As I move up in my fifth dimension, I have different ways of making identifications between points up here and points down here. And here I've illustrated two. Well, that's the coordinate freedom I have in performing, these perturbation expansions. The description in terms of integral curves and vector fields is a more geometrical way of thinking about this. And I think it conveys a very powerful picture of what this is all about. And that's all, granted to us by the 5 dimensions. I'll just finish the thought here. I know there's some questions that have arose. I'll just finish the thought, and then we can consider the questions. So the last thing I want to say is that because we have different identifications here, when I define a perturbation, I have a choice. Either I'll define to be, Q dot to be the difference between Q here and Q there, or it can be the difference between Q here and Q there. And because we're talking about two different points on the perturbed manifold, those perturbations will be different, but they will be equivalent because, I do have this freedom of identification, granted to me. So there's no unique way of doing this, and therefore there's no unique sense in which we have a perturbation up here. So the comparison really depends on how I choose to do this. We can ask about, differences in perturbation. So suppose that I take a perturbation defined through this set of integral curves and a perturbation defined through that. So I have a Q dot for phi and I have a Q dot for psi. And that simply is, the difference between this and that, and the difference between this and that. So it's a difference of differences. If I calculate this, well, that's going to be the Lie derivative with respect to V. This is that. This is going to be the Lie derivative with respect to W. The difference in Lie derivatives is a Lie derivative with respect to the difference in the two vectors. When you evaluate this and that difference, I'm calling that big psi over here. When you evaluate this on the background manifold, you need to think a little bit about this and convince yourself. But that vector C evaluated on the background manifold is actually tangent to the manifold, tangent to the background manifold. And here's the usual transformation law between two perturbations under two different gauge conditions or two different coordinate conditions. It's always given as the Lie derivative of the tensor. The reason for this comes out, loud and clear through this construction, whereas otherwise this has to be, done, through a calculation that doesn't really illuminate what you're doing. So the geometrical view on gauge transformations through Lie differentiation along vector fields in the 5th dimension, I think gives us a very, compelling conceptual basis to understand all of this. And again, I won't insist on that because, I tend to focus more on practical matters, but I think this conveys a nice, a nice geometrical picture of things. And at this stage, I think it's time to stop. And I will just say that tomorrow we'll start again, but now do something really practical. And we'll look at all of this, starting with the Schwarzschild black hole, starting with the Schwarzschild spacetime as a background spacetime. So thank you for your attention. And I think there were some questions that people wanted to ask.
Yeah, thanks. Thanks a lot, Professor Poisson. I think there were a couple of questions on the last part. One was by Sajad. Sajad, can you go ahead and ask?
Yep, don't be shy.
Yeah, so I just wanted to clarify. So this, I mean, these submanifolds, they are just the special cases of this phi lambda. Is it right?
Sorry, say again?
So I'm saying that, can you go to the previous slide?
Yep.
Yeah, so we have these, I mean, different points on these submanifolds, this P0, then P lambda, P epsilon. So then, I mean, if we talk in terms of this integral curves, phi lambda, these, so this is just, I mean, this P0, P lambda, P epsilon are then special cases of this phi lambda. Is it right to say like that?
You're saying special cases or spatial cases?
Yes, spatial case.
Okay, so you have to think of each line here is actually a four-dimensional submanifold, right? So this lives in 5 dimensions. So each line here is a four-dimensional submanifold, and that four-dimensional submanifold contains time and space. And here we're moving in a fictitious 5th dimension that's described by lambda. And as we move up in lambda, we're moving through this succession of different spacetimes until we reach the actual perturbed spacetime up here.
Okay, thank you.
And the way I move is through the integral curves of that vector field, which points purely in that 5th dimension. Does that clarify things?
Yeah, thanks.
Okay, good.
Yeah, related to that, there was a quick question whether you can explain the justification to choose lambda as another space-time coordinate.
So yeah, that's the strangeness of this whole business, right? So it's not a space-time coordinate. So we're treating it differently. So it's not part of the space-time aspect of the manifold. We're giving the manifold, not the metric, we're giving the manifold an extra dimension. And that dimension doesn't have a space-like or a time-like character. It doesn't have any of this. There's no metric information, as we go up in lambda. So it's entirely a sort of abstract dimension that is the dimension of, cranking up the perturbation to its full value as we proceed from the background spacetime. So it's a little bit strange to think about this because, me too, I would be tempted to think that if we're talking about 5 dimensions, we should include additional metric components in those dimensions, but we don't do that. I mean, so the metric is 4-dimensional, but the manifold is 5-dimensional, and that's the subtlety of the construction here that you need to sort of come to grips with.
So, Professor Poisson, I had a question actually on the same aspect, this geometrical aspect that you discussed. So there's a very old paper by Bob Garrow called as Limits of Space-Times,
right,
where he essentially discusses a very similar set of issues concerned with what happens when you try to take limits of a given space-time, such as Schwarzschild de Sitter, by naively taking a parameter going to 0 or infinity. Is this setup sort of the prescription of identifying points on different perturbed manifolds? Is it the same as what Garrow was talking about?
Yes. So, and thank you for pointing this out, because I should have given Garrow credit for this construction. I think a lot of those ideas came from him, and they were worked on by other people, and there was a body of work associated with that. But I think it's true that Garrow came up with this view of things, so it all originates from him. But you're right, sometimes there are singularities in the construction, so you can encounter situations where those derivatives are not actually defined. Those lambda derivatives are not actually defined when they're evaluated down here. Now, I think I'm not an expert in this, and I personally never encountered those situations where the perturbation theory would break down, but I'm aware that it can happen in some, I think, exotic situations. but frankly, I don't know what those are. So I have not encountered, examples of this. But yes, I'm aware that Garrosh made those warnings, and that sometimes this construction breaks down because of singularities, so that there could be singular situations that arise that prevent you from carrying this out.
Yeah, and a not unrelated question to that is, I mean, does this geometrical viewpoint help with large gauge transformations vis-a-vis the standard perturbation theory approach that you discussed before? I mean, does it give any?
You're talking about large gauge transformations?
Large gauge transformations. So, for example, at the first order, you get Lie derivatives, like you demonstrated. So, at higher orders, do you expect to get something like an exponentiated Lie derivative to describe a large gauge transformation? If you
so if you were to sum the series,
if you, for example, try to, yes, in a sense, if it was possible to sum, then
so in a formal sense, you can. I think it's true that in a sense, what you're generating here is an exponential. So as you keep adding terms in the series, you're in a sense constructing the exponentiated Lie derivative. I think there might be some technical complications to that. I don't think it's quite that, but it's something close to that. I think the main issue is, well, it would become the exponentiated Lie derivative if the series actually converged. And as we discussed before, there's really no guarantee, and in fact, it's probably unlikely that any of those series converge to anything. So those are asymptotic series. So, so in that sense, I'm not sure if it's really that helpful to think of this as the exponentiated Lie derivative. But yeah, in a formal sense, I think there's a nice packaging that you can put together that would allow you to write this out formally, at least to all orders in lambda. And there's some papers that discuss that, discuss the structure of this at any order in perturbation theory.
Okay.
Yeah, in my mind, this is this is nice on a conceptual basis. I don't think it's that helpful on a practical level, but sometimes you get boiled down at the practical level with conceptual issues. And when that happens, it's usually good to go back and take a broader view of things. And I think the geometrical view can help clarifying conceptual aspects, even when you're doing practical things. It's easy to get stuck with conceptual matters, even when you do practical things.
Yeah, thank you, Professor Poisson. There seems to be a couple of quick questions. Can we take those?
Yeah.
Yeah, so there is, I will just read out both the questions because they seem to be on the same topic.
Okay.
The first one is, why is the 5D manifold that you discuss supposed to be a manifold with boundary?
Oh, yes.
And the second...
Yeah, let me answer that right now. So I didn't stress the point before. It's simply that, the manifold starts here and it ends here. Well, in principle, this one could be pushed beyond. So in that sense, this boundary is not essential, but this boundary is, right? So the 5-dimensional manifold really stops somewhere. It stops down here with the unperturbed space-time, and that creates a manifold with a boundary. But that's not a very important point, I don't think.
Mm-hmm. And the second question was, how do you see that V minus W is tangent to the background manifold? I think it's the point, the point on this slide.
Yes, let's see if I can recreate the argument. I don't think I will be able to. So, let's see, C is the difference between two vector fields, and the two vector fields are proceeding transverse to, so the two vectors are pointing transverse to that line over here, to the background manifold. And when you take the difference, I think you can sort of see it geometrically. So you have one vector pointing along this line, the other vector pointing along that line. If you take the difference is going to be, well, you can sort of see it geometrically. The difference is going to be pointing in the same direction as that line over here. And that has to do with the fact that I'm using the same parameterization in lambda, so that in a sense, the length of the vectors are the same. So when you take the difference is going to be tangent to the background manifold. Now, there's a computation that goes with this. So the idea is only suggestive, but I think you can sort of see it, and you can confirm this with the calculation that shows that indeed the difference evaluated down here is actually tangent to the manifold. So this vector field here in the Lie derivative is actually a vector field that lives in the background spacetime.
Yeah, so there is one question from Harkirat. Harkirat, I'll just allow you to speak. So can you just ask the question?
Hello, am I audible?
Yes,
Yep.
yes.
Okay, so this geometrical construction looks really analogous to how the gauge systems are understood in the phase space. So for example, constraint surface being the physical space and gauge trajectories taking one phase space point to other physically equivalent phase space point. So basically the Lagrange multiplier, we change the Lagrange multiplier from lambda. So that is also lambda in that notation, from one lambda to other lambda. Would you like to comment how same or different these constructions are?
I think that's a wonderful observation. That's not something that I've thought about because I rarely do Hamiltonian mechanics, so I haven't thought very much about the connections between the two. But I think you're right that there's certainly some very strong connections between the two contexts. And of course, when you do phase space Hamiltonian mechanics, there's a lot of geometrical ideas that apply, and so the differential geometry of the two situations are very similar. Of course, they're different because we don't have a metric space in the case of phase space. It's a symplectic space. So there's some differences like that. But I think you're right that there's a very strong analogy between the two constructions. So yeah, thank you for sharing that. That's a nice observation.
Okay, thank you. Thank you.
Thanks, Harkirat. So are there any other questions for Professor Poisson?
So,
yeah, sure.
Yeah, Daud, if I may ask very quickly, so Professor Poisson, coming back to this log things, if I may ask, while there are like many ways to deal with them consistently in various approaches, how harmless these are?
So I don't think they create much harm. I mean, it's just that, so the context for this that I'm aware of is in post-Newtonian theory, when as you keep on generating corrections of order V over C squared, you find that up to a certain, after a certain order, the simple power expansion no longer works. So you would end up with equations that don't make any sense. And in order to repair that, you have to introduce log terms in the expansion. So you would have log V over C type terms. And I don't think they create much harm. I mean, they would create harm in the sense of if you wanted to prove convergence, for example, they would probably spoil any attempt to prove convergence for those series. But for me, that's not a big issue. So beyond that, I don't think they create much harm. It's just that they need to be recognized, they need to be understood. Sometimes there's an interesting substructure that comes from the log terms, and people have spent a lot of time trying to identify what that substructure is. But yeah, it's not, to me, it's not a big deal. It's just a fact of life that, straightforward power expansions sometimes are not adequate, and you need to, add more stuff to make it work. But probably somebody who's more of an expert in post-Newtonian methods might have a much more interesting discussion on this point. And maybe there's something about the log terms that that is intrinsically a lot more interesting than what I'm describing, but I haven't seen that.
Okay, thanks.
So it's probably time for dinner.
Yeah, so I don't think there are any other questions. So we'll all just thank Professor Poisson for a wonderful lecture.
Yeah, so thank you for your attention and thank you for all the questions. I mean, that was great. I mean, I really enjoyed this, this exchange, and I hope that you're encouraged to continue doing that tomorrow. And, you know, we should have a fun time tomorrow as well.
Thank you. Thank you very much for your lecture.
Okay, so have a good evening and I'll see you tomorrow.
Yeah. Have a good day. Bye.
Bye-bye.
Bye.